Welcome to webinar with ClampOn. Today we will talk about sand monitoring. First part is gathering the data, presented by Andreas Nordvik, and second part is understanding the data, presented by Åsmund Bakke. My name is Tonje Dahl and I will run this event. During the presentations, you may post your questions in the Q&A chat, and we will do our best to answer after each presentation. Recording will be made of this webinar, and a link to this will be sent to you. The recording will include written answers to all questions. So remember to post your questions, and we will do our best to answer. And you may also contact us at sales@ClampOn if we do not have time to answer all questions. Andreas is our first presenter. He is Area Sales Manager for Northern Europe. And I will now leave the scene to Andreas. Are you ready, Andreas?
Yes, I'm ready, Tonje. Thank you for the introduction. Hi, everyone. Thank you for joining in. I am happy to present to you sand monitoring and gathering the data. I'm glad that so many of you were able to join in. Now let's dig into the topic here. First of all, the working principle. ClampOn utilizes ultrasonic frequencies to detect sand. Here you see a spectrum where you have acoustic hearable sound in the range of 20 to 20 kilohertz. This is the same as the microphone here in front of me can detect. From above 20 kilohertz, you have ultrasound, and this is where our sensors are detecting the signal from the particles. So you have the sensor, which detects the ultrasound generated by the particles hitting the pipe wall, like this. It is mixed in with the multi-phase flow, commonly, and then hitting the side of the pipe wall in a band. This will generate an ultrasonic frequency, which our detectors pick up. The signal is then filtered to remove the low frequencies containing the most unwanted mechanical noise and the higher frequencies. You have background noise, commonly from the flow itself, also from other external sources. This needs to be filtered so you detect only the particles. Here you see a typical signal which comes from our detector. We call it a raw signal. We have a level, which we call the zero level. So below this line is only background noise, and this is defined. We also use the step value to calculate the sand rate like this. So we take the raw signal and we subtract the zero level, the background noise, and we divide by the step value. And we square all the variables so you get the real sand rate. The zero level is manually set up and managed. It's also common to use auto zero level, but this also needs follow-up. We have standard step values, and this is also able to be calibrated. So our sensors is working like a microphone, just as I have in front of me. However, it detects the ultrasound. And together with the production data, the velocity of the flow, we can vary the zero and the step level according to preset tables or to calibrated equipment. as you see on the right picture here, we have a reference level, and that gives you the 0 and step value. Now we go into the installation. The installation here is top side, and it's easy to install. It's involving no cutting or welding, and it's clamped on outside the pipe. This gives you the real-time reading. The model on the right here is only a model, because usually we place our sensors on the outside of the band, as I will show you in the next slide. So now we look into the most suitable locations. Here you have a flow line with several bands, and you have several considerations to be done. The first one is noise levels from other sources, the background noise. This should be as low as possible. However, you need to consider whether the installation should be upstream or downstream of the choke valve. And also if there's easy access and clearance from the installation point, so you can do the operation and maintenance. The first and best location would be here, from a vertical up to horizontal in the band. And this is because the particles will mix together with the multi-phase flow, and that gives you a more even distribution where the particles will hit the metal pipe. The second wanted location is a vertical down to horizontal. This also will give you some mixing of the particles, and then the energy from the particle hitting the wall will be also detectable here. And you have also this third preference order installation points: horizontal to horizontal, horizontal to vertical, or horizontal to vertical down. So here you see the installation point. It should be between 1 and 3 diameters downstream of the flow. And you could have this larger radius bands or this smaller radius bands. The illustration gives you the best, the area where you can fit the sensors. So when the impact of a particle hits the metal on the pipe, the signal will travel in the metal itself. It's a good conductor, we say, for ultrasonic frequencies. Now let's dive down and into the subsea world. This is the new ClampOn standard funnel. This will be released early next year, and it will replace what we call the common compact funnel. So it utilizes the same principle. It's clamped on outside the pipe and bolted with 2 bolts, as you see here. The picture on the right, you see a sensor which is placed in the funnel with those pins, and is fitted by turning the ROV handle, the orange handle here, and turning approximately 45 degrees. So this funnel is well proven and a good starting point, but sometimes you want to fit and place a sensor and funnel after you have put all the parts subsea. But then you probably, or often you want to install by diver, and this is a challenge because you have loose parts and bolts and nuts during assembly, which is not very diver friendly. So we have a solution for that as well. We have this diver installable funnel, and this is a pre-assemble somewhat, so we have connected and preset the bolt to the right tightening, and we have no loose parts, and you have this open slot hole. So I will show you here a video of my colleague Vidar, who has designed this. So you have just enough gap to place it around the pipe. This black material here is an adapter only for testing. So you have this longer bolt to get a larger gap to place it around the pipe. So you have to tighten a bit further here. And then he will use this torque wrench to get the right torque for a good connection. So you can see this is not coated yet because this is only a test, and he places this test sensor within. So you see you have a good fit of all parts involved. If you have a deeper water, you might need to install by ROV, and this is our solution for that. You have a ROV retrofit funnel. This can be either temporary or permanent. You grip the pipe by turning the ROV handle on the right here. So the ROV ROV funnel is also protected with corrosion protection from an anode, which you see on the outermost gray block below the ROV handle here. And this is applicable for all of our passive acoustic applications. And it can be done for greenfield and brownfield. When you install a retrofit, you need to remove some coating. Our sensors needs metal-to-metal contact to work. So that's why we have created this cleaning tool. And this has a soft milling bit, as you can see in the brown color on the front here, on the tip. This will make sure that only the coating will be removed, and it's not damaging the metal underneath. So, and this can be used in all fixtures, and also for non-retrofit or temporary, where coating has not been removed. In front, that is. Now we go into implementation and communication, which is maybe more connected with the gathering the data, the title of this presentation. So as you can see on the left here, you see the standard sensor with a side entry where you have an oil-filled hose or a cable together with a connector. This connector is then fitted onto the subsea control module, the SCM. If you don't have room or for any other reason you can't have the side entry, we have the bulkhead sensor, which is a top entry with the cable connected on the top. Now let's see a little video here. Here you see the flex funnel. This is then fitted with a sand sensor and then a side entry hose. So you place the sensor by turning your ROV handle, and the front will get metal-to-metal contact with the pipe. Here you see a transparent view with the 3 springs. This gives approximately 30 kilos of force to the pipe, which ensures a good contact. Here you see a subsea control module. This has a sensor placed on the bend, and then you have the hose connected with a long cable here. Here you see a transparent view with a flow with particles, and on top of my head you see this graph, which is a representation of the raw signal here. This hose is then connected here. Here you see the connectors, and it's fitted onto the subsea control module like this. Yes, so now, as I have already presented, on the left here you see the standard compact sensor. However, this is not our first initial design. Our first design was this middle one, which is called the deep water sensor. This one is installed in many fields, and if you have this and you want to switch for whatever reason, maybe you would like to measure vibration as well as sand or pig, then you could make the switch by using our compact to deep water adapter. This adapter is fitted on the outside of the compact sensor, as you can see on the left picture, which makes it able to be placed within the deep water funnel or fixture. This will also work the same principle if you want to place our ClampOn sensors within other companies' fixtures. So we are able to adapt to whichever fixture you have. So when it comes to gathering the data, as you saw on the previous movie, the picture on the right here is a subsea control module with a sensor on the bend here, and then below you see the orange cable. You see also one cable here going to corrosion erosion monitor. On the left there you see some schemes. So you have, for example, 3 sensors, which is then talking to the subsea control module and then sending the data upwards to the topside control module. The topside control module could, as an option, have the ClampOn computer with the software, and it's also optional to send the data offshore with the online monitoring link, and this makes it able to talk to the onshore people. Also, we have support at ClampOn, which can help you analyzing the data. This the next presenter will talk a little bit more about. So if you don't have room in subsea control module, and or if you don't have power available, this is a field case where we have a portable subsea acoustic sand monitoring system. This is battery powered, and then it has data storage. It can be installed with ROV, and in this case it was 40 days of operation. So we have several solutions if you don't have the common system in place. This is a collaboration we did with ProServe. So here it was 3 vibration monitors, and we got the power, and the signal was transmitted through this power line in one single pair cable. And you can see here, as it says on the PowerPoint, 16 kilometers of umbilical, so very long distances. Here is another collaboration with ProServe. This was a corrosion erosion monitor, a CEM. You see on the picture on my shoulder here, this is a CEM in a band, and you see the canister on the upper left of that picture. That signal was then piggybacked through this power line modem, which gave direct communication through umbilical, independent of the SPS system. This case was 19.3 kilometers of umbilical, and also it was powered, and communication was modulated over this single pair. So I hope you enjoyed watching this presentation. I want to thank my colleague Leander, who made most of these illustrations for me. And yeah, thank you for listening in. Do you have any questions for me, Tonja?
Thank you, Andreas. Yes, we do have questions. I will start with the first one. It's from Stefan, and he says, "Hi, will the new funnel be capable to be installed within a band as well as afterband, tight band? And is it usable with insulation? So kind of one size fits all."
Yeah, so the common standard funnel here, that can be also installed in a band. I don't know if you would have the same that would fit in this band. However, we will have a solution for that as well. If it's not the same mechanical funnel, it will be a different one. So we will look into it and give you the correct answer after the presentations here.
Thank you, Andreas. And to follow up on this question, depending on answer to earlier question, yeah, when to use standard and when to use the flex funnel.
So we would like you to use only the standard funnel. The flex funnel is going out, and yeah, the new one will be better to use.
Thank you. Going on to the next question. Any experience in detecting sand, silica, earth with ClampOn silica particles of mechanical pre-treated straw of minced bales in conveyors of onshore the biochannel plant?
Could you repeat that?
I will repeat.
Thank you, Tom.
Any experience in detecting sand, silica, with ClampOn silica particles of mechanical pre-treated straw of minced bales in conveyors of onshore the biochannel plant?
Okay, so I picked up a few variations of the particle. So the importance is that the particles is solid and hitting the metal pipe wall. So it can be different types of particle. Maybe you have normal sand, or maybe you have a different solid. And then it was another question in there, or variation, which was a plant. Tonje, can you repeat the last part?
I think the question is that they have a bioethanol plant and they have the, what does it say, background noise is very high for these plants, and how to monitor there. I think maybe we will get back to this in writing to get the correct answer.
Yeah, so the background noise could be an issue. However, we have good experienced people here that could support you in that. We can detect particles in all metal plants or metal piped plants where we can place our sensors in to fine tune it and get it accurate. That is important to consult our support team.
Thank you. We go on to the next question. What type of engineering unit is the raw value?
The raw value is unitless, so it comes from calibration and this formula, what will be the sand rate. So if you can remember, it was the raw value minus the zero level, which was the background noise, and then we divide by the step value. That gives us the sand rate when we square all the variables there.
Thank you, Andreas. Moving on to the next question. Is it possible to separate between noise from sand fines, particles, and liquid drops in a gas stream?
So liquid grumps, I am not familiar with that, but you have a good filter on our sensor. The signal frequencies of, for instance, gas or water or sand, it's very special, and we use the band filters to filter out the unwanted noise. So we are very experienced with filtering out only the sand. However, if it's some sort of other solid particle, it will be detected as sand as well. So we don't do variations of different types of particles.
Thank you. Moving on to Jack has a question. Any limitation on the umbilical length?
That depends on the protocol you're running on. So if you have a can open, I think it's around 40 meters. We recommend not to go above. And then if you have RS 485 communication with the Modbus, then you can have longer distances. However, as you saw in my presentation, we have solutions that could extend this range. So just get in touch with us and consult us if you are on those borders, and we will help you out.
Thank you. Next question. Also, any limit to how deep the ClampOn subsea can be placed?
So our compact sensor is up to 3,000 meters or 10,000 feet.
Thank you. I have one question here. How to have control on sand rates for subsea ASD where it is not possible to do calibration?
I'm guessing you know about sand injections, and this is typically done to calibrate that table with the step and zero levels, as you saw in the beginning of my presentation. The sensors we send from our factory is pre-calibrated, and as you know, it's more accurate with sand injection. So this is not possible subsea, only topside. However, you could utilize our experience by looking at the sand data and also the multiple of deliveries we had worldwide. And I think we can see that it will be accurate enough for its application.
Thank you. I do believe we have time to 1 or 2 more questions before we change the speaker. Those questions that we are not able to answer now will be sent to you in writing after the event. So next question here. We have battery-powered sensors for subsea. Are there plans to produce battery-powered sensors for topside as well?
Very good question. So we have in our portfolio coming up, it's a ClampOn bird, we call it. It will be battery powered and wireless. This is in a development stage. We have presented it somewhere around different expeditions, and yeah, so this will be available soon.
Thank you, Andreas. We will now change the scene to give the word to next presenter. We are now getting ready to continue with Åsmund Bakke. Åsmund is the manager for service and support in ClampOn. He has been with ClampOn for some 20 years and is an expert in sand. I will now leave the scene to Åsmund.
Yes, thank you, Tonja. I think it's wrong. Yes, thank you. Yes, one thing is to have a ClampOn instrument installed. Another thing is to use it for what it's worth and also understand the data. So that's what I'm trying to explain you now in 20 minutes. So could talk for days about this, but I try my best to do it short. So the thing I'm going to talk about is who is using the sand data and how sand management, and this is connected because how the operator are dealing with sand is also deciding how the system should be and who should be able to read and work with the data. I will also find some typical sand signal and show you some events and talk also about accuracy, which is also depending on your sand management or the sand strategy, etc., which is different from companies to companies. So when I'm talking about ClampOn data, I talk about ASD, which is acoustic sand detectors, and CEM, which is corrosion erosion monitor. What we can see is that these two instruments, they are perfect together to be able to, the ASD, the acoustic sand detector, to actually measure the sand in real time, and the CEM actually to monitor if you have any sand production and you have erosion, so actually monitoring the wall thickness loss. So if you have high risk wells, that means high velocity gas wells, etc., and the combination of a sand detector and a CEM is perfect. What we see as best practice now when it comes to a sand and CEM system and who is working with it and how to work with it is that you have the platform here, which need an alarm from these instrument systems, but then you also have an onshore team in the company which work more with this data and look after it and use it into erosion calculation, etc. And the best model here is that ClampOn service and support are talking with both platform and the onshore team. So this figure here illustrates this CEM, this instrument which can monitor the wall thickness in the area between these two transducer rings. And here you can see the ASD, the sand detector. And these two instruments should give an alarm to the operator on the platform or on the plant. And the update frequency of these data don't need to be very high, but it's very important that the alarm is transferred and the alarm is a real alarm. And of course, the operator should know what to do. For the onshore team, they need also these data, and I listed up all tags they need, because onshore in the data center, they're able to recalculate, they are able to use this data into other models, etc. And then the data should have high update frequency. For example, 1 second from the ASD, which is the normal updating frequency for the sand detector. ClampOn service should also have a remote access to the instrument for maintenance and support. So how are they working with the data? The operator, as I mentioned, need an alarm if you get a sand event. Maybe they, if they have an event, want to trend it, etc. And this sand and CEM system is very important for the safety. If you talk about a gas well at 40 meters per second, if you get a real sand event, you can have a big issue after a half hour. So it's important that it's real-time data. When it comes to the onshore team, they use our data in their production planning. They are responsible for the sand management plan and the strategy. They use the data into erosion models. If they had any event, they can use this data to understand why a valve is broken, etc. But in good sand management, that doesn't happen, because then they actually monitor the sand, so they avoid destroying any valves, chalk, etc. When it comes to portable systems, then we have the possibility to, you see the sensor illustrated down here, the acoustic sand detector with a vibration sensor as well, can be connected directly to a cloud solution. So the data are transferred directly to the cloud, and then we can sit onshore in the office, at home, on the mobile phone or on the platform and monitor this in real time. So for the future, maybe also the permanent system will be designed like this, because then other systems on the platform can take the use of our data into virtual meters, etc. So yeah. When it comes to sand management, I already mentioned that this is different from company to company, and it's a wide topic, and it has changed a lot during the last 15 to 20 years. I remember 20 years ago, a very common comment was that, oh, the ASD doesn't work, I don't understand it, it's strange. but it has changed now until that actually they don't produce without having signal from the ASD. So it's been a big change. Sand management, it takes time, but you get so much back for it. I have some terms here. It's called ASR, that means acceptable sand rates. This means maximum sand-free rates. And I'll talk more about that later. But when it comes to sand management, you also have sand handling, erosion, of course, sand transport, screen failure, but maybe also the main thing, by doing this correct, you can increase your production. So ClampOn has a small but very important role in this, and it's very different how this is done. So in older days, without a sand management plan, very often they control their production by using the sand trap. They were actually routing the wells to a sand trap and look into the trap, or maybe they used manual sampling and checked if they had sand or not. And that decided if they want to increase the production or not. Then by installing an ASD, possible to monitor it real time 24/7, we got a new term called maximum sand-free rate. They could actually look on the ASD and use that to control the production rate. And then the whole business has developed even more with acceptable sand rate. That means they can allow some sand because we are able to measure it so accurate. So after, for example, 30 years, it's no problem if your pipe is eroded a few millimeters, as long as you don't have to replace it earlier than 30 years. So by doing a good sand management work, using the ClampOn sensors, you can increase your production a lot. Maybe not well by the rate this much as I illustrate here, but you don't have this much downtime. You don't need to replace your chalk, etc. So you get a more stable and predictable flow. Our role is to keep the ClampOn system up to date, make sure that the zero levels are correct, that the conversion from raw value to sand rate, that means this step factor, is as accurate as possible. It was a question to Andreas here about the subsea topside and how to calibrate subsea. There are different projects going on there, but one thing we have done there is indirect calibration, where we have calibrated the topside detector and used these data for the subsea sensor to indirect calibrate it. But by having a support contract, we are maintaining the system, we are reviewing the data. Sometimes there are unwanted noise from chalk, other external sources, etc., which we can remove. Then reporting to our client, of course, talk with our client, and then always optimizing the system, how to get it more accurate and better. A very important factor when we're having a support contract is that the operator should have ownership to the system. They should not just let us work with the data. So we have to work together to get the best out of it. Yes, then over to typical sand signal and event. We are monitoring more than over 1,000 wells real time here from our office in Bergen. And most of the wells are close to sand free, and it's very easy to understand what's going on. We don't have to use much time on it. But we also have wells which have a more changeable gas liquid ratio, external noise from other sources, etc., which makes things more difficult. Also, high viscosity can be an issue. We can see that sand production very often is related to startup and water production. We can also see that many wells are sand-free until a given rate. We have also seen a thing regarding screen and completion failure, that you have a sand-free well, suddenly things are changing and you get sand production. So when having a sand alarm, is this real sand production? The first question you should ask yourself is, are the raw value fluctuating, or is it pretty stable? And how does this event start and end? Maybe you are in the middle of it, so you don't know the end, but then look into the start, how it starts. Is there anything else going on the same time? this can be valuable information. Typical sand signal, that's amplitudes going up from a baseline with a different magnitude. If the magnitude are about the same, then it's probably noise from something, but normally sand, you have a magnitude which varies with a big difference. That's because particles, sand particles, they have different size and they are traveling with different velocity up, so you get a very typical signature of that signal. So now I plan to show you some data. This software is called Sand Analyzer. And as you can see here, the blue color, that's the raw value from the sensor. This raw value is updated every second from the sensor. And the data I'm going to show now is a typical startup. So as you see here, the startup here, you see the black line coming up. That is the flow velocity. That's calculated based on the gas, oil, and water rate, pressure, and temperature. And we know the inner diameter of the flow line and calculate actually the velocity. So as you see here, when I start up, you see here on the blue line, you suddenly get some response. That's a good sign. The microphone has contact to the flow line. There are happening things in the flow line. So these amplitudes going up here shows that there are traces of sand coming up, but not much. This is a gas well, and as you can see, the velocity is about 8 meters per second. We know that to lift sand particles, if in a gas well, you need to be somewhere here to be able to lift solids, somewhere between 6, 7, 8, 10 meters per second, depending on the size of the particles. And as you see here, it's coming a little bit sand here. And then the operator here chose to close the well, as you see. And then the question to us, this was the first startup, is how much sand is this? And then Andreas showed you the formula and how to calculate sand. Try to show it here in direct how it's done in practice, because you see that the background noise level here is about 3,900. That's the zone level with no sand. The point here is that all values above this line here now is sand. Should be calculated by the system as sand. And then by using this zero, we calculate how much sand this is. And as you can see here, we talk about 430 grams of sand. So it's not high sand production. So then I'm using this zero level for the rest of the startup as a reference, and then the well is opened up again, and you see here we get a small sand event again, and here they start up more and increase the velocity, and you get even more sand. But this is a typical good sign. You get some solids up, but it's reduced. So this is for sure some sand. Same here, they increase the rate. It takes some time, maybe the bottom of time. Get sand, it's reduced. And then as you see here, it develops. They increase the rate, they get up solids, they wait, and it's reduced. And it's a good way of doing it. And to the end here, they're up to 80 meters per second. They still have sand signal here, but not very high. And most likely after a few more hours, it will go down and be close to zero. So typical sand signal, look here, amplitudes going up from a baseline with different magnitude in a randomly frequency. Yes, this slide here shows also a typical startup. And as we can see here, the raw value level is up to 100,000. And you see a really high spike here. We got a lot of phone calls to the support center when they are here. They got a really high raw value, and I'm wondering what's wrong. Here they have maybe 2-3% chalk, really high pressure over the chalk, and you have really noisy sound from the chalk. So this is no sand, it's actually noise from the chalk. As you see here, black line again is the calculated flow velocity, the blue color is the raw value, and as you see, as they chalk up, the noise is reduced from the chalk. And then when they actually came up to 60 meters per second here, we can see that they actually also have some small sand production. We talk about 300-400 grams for this the whole period here. So it's very sensitive instrument. Just as an illustration, imagine that you are producing at 17 meters per second. If you have 1 gram per second, then you have on 17 meters on your pipe, you have 1 gram there. That describes a little bit how sensitive the instrument is. This is another example. Client called us and had a lot of wells. Each trend here is a well with ASD. They had produced for years with no sand at all. Suddenly they got sand on all wells on the same time. You can see on the same time here something happened. And then by investigating this, a lot of meetings, etc., we found out that all wells had a common mag injection tank, and they had mag injection on all wells. So they got solids into the mag injection system. So they actually started to inject solids in the mag into all the wells on the same time. So by cleaning that out, they was rid of the sand production. This is another example just to let you know that it's very important to understand that we have different wells, and we have to actually read the data and know where your sensor is installed, etc., to be aware of how high the signal can be and how much sand it can be. In this case here, we had a subsea sensor installed on a horizontal to horizontal band. That means that the solids are in the liquid in the flow. That means we should use the liquid velocity when thinking of how much sand it is. And the system itself gave an alarm here. You got an event here, and then a new one here, and I couldn't understand what happened. But as you see here, we measured it to be almost 400 kilo. But when they opened the separator, it was almost filled up. So here we have underestimated the amount of sand. So you should be aware of all parameters when looking into the sand data. When it comes to this example, it's an example of a water breakthrough. Wells have produced for years with traces of sand, no big deal. Then suddenly we could see a big change in the signal here, and this was increased water production, but also increased sand production. After a week or two here, this well was dead actually. So what about accuracy? I mentioned it regarding sand management and sand strategy. That decide what accuracy you need, and an important thing is that the users of the system need to know it, and it should be considered in the project phase, because the accuracy depends on how your system is set up. But this change, we have seen that the last 20 years. Systems we delivered 20 years ago now is possible to get very accurate, but then we need to do changes in the system. But of course, it's always cheapest to do it right the first time. So to have accurate output, it means correct configure system, but also remember maintenance and knowledge. When I talk about maintenance, the physical thing is if you have topside detectors, make sure that they have proper contact to the flow line. If not, it's not that sensitive. Other thing with maintenance is, of course, to make sure that the zero management is correct, that your software use correct zero. If you have auto zero, it's set up correct, etc. And also, of course, that knowledge personnel are looking into your system and make sure it works as it should. When it comes to accuracy, I've categorized it in 3 different categories here. If we are talking about a system, sand or no sand, that means if we go back to the sand trap I showed, that more like if you have sand or not, it can replace the sand trap. And the only thing we need then is the raw value. Because if it's flat, no fluctuation, no issue, no sand. The problem is if you start to produce sand and you have a system like this, you have a big issue, because then you have to start collecting what is the velocity, start calculating the sand rate, etc. And it's not possible to implement that in the system in a day or two. It takes time to change things, how it's integrated to the control system, etc. The next category here is traffic light, which is the most common way of accuracy for our systems. That means that our system has a production data input, so we calculate the velocity. I would say that by having being in this category, you can use it to find maximum sand-free rate. Then we use the standard step table. That means it's not calibrated by sand injection. And this standard step table, which converts it from raw value to sand rate, is conservative and often good enough. And to say it in another way, if you're under the sand rate you are allowed to produce with this with the standard step, it's good enough. It's it's conservative. Over to high accuracy here. That's then we also need a raw value, velocity, but then calibrated by sand injection. Then the system become very, very accurate. It's hard to talk about percent, but 2, 3, 4, 5% accuracy. This is needed if you are controlling your wells by acceptable sand rate, and you are up to the limit of what you are allowed to produce, and you want to see if you can produce on even higher rate, and maybe your system is too conservative. Then sand injection is a good idea. It's always important also to say that sand injection is done also to do a verification of your system to make sure that it actually works, because we have seen systems where you are producing on too low velocity, too small particles, maybe viscosity in the liquid, and you think you have an ASD system which works, but the sum of these factors cause that the particles are not detected. So the instrument itself, the ASD, is acoustic sensor, which is very accurate. What I'm talking about here is the accuracy for the sand rate. Over to the CEM, the corrosion erosion monitor. That measurement can vary up to 1% of the wall thickness, and the number of pads, that means how many transducers you have, will decide the total coverage of the band. So that's a thing to consider when you are in the project phase. Yes, so hopefully in this 20 minutes you have understand that by using ASD system, and if you also use it for what it's worth, you can earn a lot of money. You can instead of replacing your choke, downtime to change valves, etc., you can control it 24/7 by the ASD. But it takes time, and maybe you need help from us in ClampOn.
Thank you, Åsmund. Good presentation, and let's just get straight to the questions. First one out now is from Edward. How far off, in your opinion, is the cloud solution, and are there any large technical issues that you need to solve?
Yes, the cloud solution is already here. We have a cloud solution in use for portable systems. When it comes to for permanent systems, we have, of course, an issue with cyber security, because our system is also an alarm for the control room. We have to be careful with where the data can be stored and where it's transferred and what can be interfered by others. So for permanent installed systems, the cloud solutions are not there yet, and maybe it can never come regards to the alarm to the control system. But it's also possible to have that part of the system separated and then share the data out to a cloud, so it can be available for a virtual meter, etc. And for example, for our client having a support contract, we are now working on presenting the data in software, as I showed you, the sand analyzer, as a cloud solution instead of in a report, for better understanding and for better detail level in the presentation.
Thank you, Åsmund. Next question is from Santosh. Based on your expertise, can you suggest which would be the right parameter to depend on for monitoring and taking a decision to reduce the choke? Is it raw value or the sand rate, which is a calculated value?
If the system is set up correctly, you can trust the sand rate and you can use that. But if you don't have a up-to-date system, the zero is wrong, etc., then you should also look into the raw value. And if you're in doubt, you should contact us.
Thank you. Next question from Brian. We operate gas storage and the initial gas produced is dry, followed by wet gas. What is the difference noise generated by sand between dry gas and wet gas? Should different calibration settings be used for wet gas and dry gas?
Yes, we have done several tests with this at the DNV, and we can see that on dry gas, the background noise is quite low, and of course the sand response is very high. So we are very sensitive in dry gas. When it comes to wet gas, when you have a little bit condensate, not enough liquid, so it's a phase in the flow, but it's in droplet, then it's noisy and it's interfering on the same frequency as the sand. The thing we could see is that even low sand rates are still giving higher sound level than the noise. So not an issue, but we need to be very careful with this when deciding where to put your zero level. So in that situation, could be good to discuss it with us, compare it with our result from DNV, etc. So it's a typical, a little bit tricky situation.
Thank you. Moving on to the next question from Helge. Can your sand server import real-time production allocation data for flow rates, etc., from client production allocation system and use this for calculation of sand rate?
Yeah, that's a very good question, because if we go 20 years back in time, then we didn't have flow meters which could give us good flow data, and still there are many wells out there which don't have a flow meter, and we are used to use allocated well test data, and we have different solutions there, from a fixed lookup table in our software we can define it, till SQL link where we are picking up these allocation curves directly from operators database, etc. So there are many ways of doing this, and take contact again and we can together discuss what's best for you. And it's important to get as accurate input to our system as possible, because if we think the velocity is 10 meters per second and it actually is 50 meters per second, that means yeah, the sand rate is not correct.
Thank you. Moving on to next question. What if the system indicates sand production, but the sand trap did not catch any sand at all?
Yeah, I've experienced that many times. One thing is that we are detecting 24/7. That means every second we have a raw value. And when you're taking the sand trap, you often take it there for 15 minutes, 20 minutes, a half hour, etc. And very often it doesn't catch everything, maybe only 2, 3, 4% of what's in the stream. So depending on your flow conditions, maybe the sand trap doesn't get it, but also remember that the ASD maybe also detect smaller particle which is not going to the sand trap, etc. So normally, by having a close cooperation with the operator there, we find reasons for why we detect it and it's not in the sand trap.
Thank you. We have one more question now. While doing brush test for function test, do you think it is sufficient enough to only have erratic roll values as verification that the sensor is working, or should we expecting it is achieving to a certain level of RV associated to real sand alarm?
Of course, the best verification is to do sand injection topside, but it's expensive. We have to send out our equipment. We need to have two service engineers offshore, etc. And a very cheap way of testing that you actually have response from the sensor is to use a wire brush and brush on the pipe. It's not as accurate, it's not as good as sand injection, but it's definitely better than nothing. The last part of your question regarding ROV, if you have an ROV sailing, passing a sand detector, normally we pick up sound from that. And that's normal. So that's give also a erratic signal, as you mentioned in your question, almost like we are brushing on the flow line. So we are picking up sound from ROV.
Thank you, Åsmund. And that concludes our presentations today. Thank you for joining us. Hope you learned something, get some new information. We will send the recording of the event to you after this event with the questions and answers. Should you have any further questions or comments to us, please do not hesitate to contact us. You may also follow us on LinkedIn to stay updated on future events. Thank you. Bye.